Okay, so today I will be talking about these new research ideas, probably focusing mostly on 8 papers that were selected on this. A lot of them are in representation and trying to go a little bit beyond what we've seen. So we've seen, for example, also some of them mix things, like it's quantification and representation. Or one of them is fusion, transference, and generation. So we're starting to merge the topic because it's very rare that a paper will have just one novelty, like one contribution. Often the contribution comes because of many of those challenges. We, from a pedagogical perspective, try to isolate these challenges so that you understand each of them, when in reality they come together. So representation, fusion, this is a very interesting paper. Mostly the analysis was the most, is it this one? Yeah, the analysis. In fact, the next 3-4 papers are mostly, there's analysis and a proposed model or solution, but the 3 of them. So this one is, I think there was also a CVPR 2 years ago that tried to address some of it also. So that when you learn those representation, when you fuse, when you bring the multimodal, there are different challenges. The one that was, and I guess I'm blanking on the name of it, in that CVPR 2 years ago, is that modalities may learn at different time. Like if you had to pick a learning rate, it's maybe not the same learning rate for each modalities, and that will be an issue if you have a multimodal model that has the same learning rate. And that was one of the things. I would try to find the link of that CVPR 2 years ago on this. But this one was also studying the same idea of why when you train in these end-to-end model, both the fusion and each modality together, when you fuse them together under often they underperform. It seems that some modality will take over the other modality. And so you've seen it quite often, like especially models that have language in it often will rely on it mostly because each phrase is very informative. There's a lot of variability. The noise may be not as obvious. So sometimes a modality will take over. And so the other modality, the problem here that they're trying to address is not just the balancing of the modality, is that if one modality suddenly at the beginning start performing well, the other one will get less and less gradient. So it's almost the winner takes all, because it started succeeding and getting high weights at the beginning. In later stage of optimization, the second modality will just have no chance of fixing itself. It gets less of the gradient back. And that is probably something that may happen to all nonlinear fusion. That's at least what the author tried to claim. But I will not go as far. But definitely in the additive case, in additive fusion, it seems to be the case. And that somewhat makes sense. And so that's why the claim is great. The fact that they did it just for additive or primarily for additive makes the paper interesting, but not completely groundbreaking, but it at least enables some thought process about the problem. So let's do it for additive. And so if I do additive fusion, what's the simplest way to do additive fusion? So one option is to bring in the same space and then you do the additive. The other way is concatenate and one layer neural network. That's the other way. So they went for the second one. So they just concatenate and do a one layer neural network. So then every neuron is the weighted average of all the other input. So it's kind of an additive version of that. So you just concatenate and then multiply, and then you get your prediction. And it could be often just a linear here, and that's what they studied. So the output is your output, your prediction. That function that you're learning has 2 weights, the WA and WB, that just multiply each of them. Now, so that's we've seen this is additive fusion. By the way, the paper uses a different notation. So I try to use the notation we use in this class. At some point in this slides, it gets a little bit hard. And so I'm going to sometimes use their notation, which in fact, that's probably the thing with any research paper in machine learning in general. You spend 50% just understanding the notation. And once you got the notation, then the other 50% is like the real. But the hard thing of any of those papers is the notation. And so, and sometimes you're lucky because a sub-community keeps reusing the same notation, but often papers will create their own notation. So yeah, so the problem that I just mentioned is that, and that was the nice insight, is that one of the modality may end up being dominant. And in this case, what we will mean by dominant is two things. You could say one is the cause, one is the problem, but in a sense, the cause is that the weights of one of the two modality are going to just get higher. I mean, if some prediction are just more accurate, you're just going to weight them more than the others, like this, especially in the linear case. Like you just weight one. That's like linear regression 101. If you do in statistics, you want to know which features are important, do a linear regression, and then you look at the weights. Relative weights tells you which features are important. So if one of them is important, then that modality will have higher weight. Now, the part that you don't always realize is that those weights also have an impact on where the gradient goes. If there is an error here, who gets the gradient? And that was the nice insight. And so for that, it's good to look back, like this is just like typical gradient descent. So I have some weights. The T is like iteration. You're optimizing over many epochs. And so I have my previous weights, and then I have a learning and the gradient of my loss, okay? And let's say I use one of the two weights as my, so I will gradient related to one of the two weights for now. So what's interesting here, and here I'm just taking the gradient of the loss and just spill it out. So gradient of the loss or the partial derivative over my function, and then the partial derivative over the weights that I have. And so at the end of the day, updating the parameters of W will be related to FA. So mostly the WA, its error, like the way I change A is based on A itself. Like, so that's not too surprising because it's additive. So the fact that at the end of the day, what the way I will update it is based on myself. So that's just, the paper makes it as if it was surprising, but it's not surprising because they were doing additive. But the interesting part is that this is weighted by the loss based on this, the partial loss. And that one, I didn't put the whole math, the paper has the math here, but if you do the math of it, it turned out that whoever has the bigger WA will have the largest weight here. So if I want it related to WA, and WA is high, like WB is much higher, that will be reduced here. And so you get less of that weight. And so you will get less of the gradient coming down there. So the way they try to address it, and that's one proposed solution, is to say, I'm going to add another term in my updates, and what should it be? And that, like, really up in the air. There's one way to do it, and that's what they call on-the-fly gradient modulation. It's just that extra value. And how do they compute that extra value? So they look at each modality and look at the max of because you have each modality and you have their output, you look at the max of that output. And that gives you for modality A and modality B. And sorry, I didn't have time to like rewrite the whole thing, but they use, instead of like unimodal A, unimodal B, they use that notation. Instead of FA and FB, they use a different notation. But that's just the output of each unimodal predictor. And then they take a max, and then they do a ratio of it. Just a simple ratio of the two. What does the ratio give you? The ratio tells you like how much of the output of each modality, how important, like how much. In fact, it's kind of taking WA. They could have just do WA and WB and just do some kind of measure of how strong the weights are in WA and how strong the weights are in WB. But they're doing it through also taking into consideration, they do it over a batch. They take a batch and they run all of the X in that batch through the WA, and then that gets them that value, and take in that batch all the WB, the XB, and that gives a ratio. And then because that ratio can go minus infinity, plus infinity, they need to renormalize it, and that's what they use there. But the bottom line, and there's a hyperparameter like any good model. So what's really nice is that they tried it on doing baseline. They call baseline just additive fusion. They tried a few others. Film is a good one. I'm not sure we talk about it in this course, but this is a modular fusion approach that's worth exploring also. And then eventually they showed that if you reweight the gradient, then you always get an improvement, like sometimes much bigger, almost 10%. And these are just audiovisual data set that they pick for that. So it's just to give you, because often when we talk about fusion, we talk about fusion as almost an inference problem, like learning how the people interact or modality. But at the end of the day, the model, the way it learns the interaction is through the backpropagation, it's through the optimization. So really, it's not just about defining the correct objective function. It's also being sure that your learning process is correctly balancing the information. So that's kind of the take-home message I wanted to give you there. So, and they also had another novelty, but I'm not going to talk about that contribution. So also in the fusion, but this one is about as an interesting, yes. My understanding from the math is that it was, I didn't put it there, but the issue seems to be both in the fusion. And what I didn't put here is that FA also has a parameter to it, because that's your unimodal. So, and that one also has parameters. So, and in the paper, they seem to argue that this issue is both for the fusion and the unimodal. So both the fusion will get less gradient in itself, the gradient, it will get less and less gradient to be able to fix itself properly. And the main thing they argue is that this one get even less gradient, but also get less gradient. So the issue seems to be both at the fusion level, because they kind of reinforce itself, and it also at the unimodal level. Yeah. The insight is that you're doing the weighting. You're not really weighting WA and WB itself. In a sense, you're weighting the changes. So you're kind of increasing the temperature a little bit of your learning. You're kind of increasing your learning rate. So I think it's not that you're like really changing the weight themselves. I mean, you are in a sense because you're increasing your learning rate, but the intuition is it's different from a more typical taking a gate and weighting them as a business. Here, we're not doing it during inference. This is really just done during the backpropagation. And it's mostly you're kind of adjusting your learning rate dynamically based on that. So I think it does something different in this case, yeah. And it seems, at least in their experiment, that it does improve. Now, how much it generalized, we'll have to see. Yeah. Okay. Great. Okay, so the other one is fusion. So we have the same kind of fusion. Don't look at contrastive yet. This is like a typical fusion. So unimodal and then bimodal and then the prediction. But the interesting insight here was in many cases, you'd like to be able to be robust to missing data, Now, it can happen because just a modality at test time is not there, or one of the modality may be noisy, or just in general, you may want, so the robustness is kind of the intuition, but the real goal they have is they say, if you have unimodal representation, and then you have that multimodal, shouldn't they be in a somewhat similar space? Like, should they not be in similar space? And so they would like these to be in similar space. And the reason for that is that if they're already in similar space, then if suddenly at test time, one of them is not there, then at least this one will already be somewhere close to where the multimodal fusion will have been. And so how to show it visually? And that's what they say, is like, I'd like them to be aligned. They did this really nice analysis on over many data sets, but also over many models. And what they plotted this one and one of the two modality. So visual, one of the two modality, and this one. And what was interesting there is this, so it's a multimodal variational autoencoder, multimodal variational, so an autoencoder, and this is, you know, when we talk about fission, we talk about factorizing the data into modality and unimodal and multimodal. So that's multimodal factorized model, but they just compare over many different models, and all of them end up where the unimodal are not aligned with the multimodal is not aligned with the unimodal. And what they would want is more something like this, where they're overlapping, they're in the same space, they're in the same vicinity. This is what they would call in this paper align. So how do you align thing? Alignment 101, it's also in the title, contrastive learning. So what they do is they just, you want something to be aligned, just put it as close together for positive pairs and make negative pairs far from each other. And that's why you see also the clustering naturally happening here, is that they would put, they probably ran this one on the, I don't know, 8 class problem. So that's why you see it so clearly. So it was on MNIST, so 10 of them. Good. So what the typical contrastive learning, if you have negative pairs, in fact, this contrastive learning that they're proposing is specifically start with 2 negative pairs. So you have 2 different digits. One is visually seen and one is spoken. And then you, sorry for the figure, like, so what you do is learn one unimodal, and then you learn a bimodal, okay? So these are classifiers. They separated the classifier into an initial one and then a 2-step, but that part is not important. It's like you have one classifier, unimodal, one a bimodal, and one unimodal. And what they will do is just typical contrastive learning, but with this interesting twist. So they will make within the same sample, you're going to make them to be close to each other. These are going to be positive pairs. And then, so this is positive pair. And then they're going to make it so between negative sample, they will try all of them to be different from each other. So what it means is that for the same digits, then these should be close to each other, but they should be far for 2 different digits. And then they use a typical contrastive loss. So positive pairs, and this is a summation of all the negative pairs. Negative pairs are all the different version of that. So, so that was a cute idea. And another idea also at the middle of quantifying and fusion also that I like quite a bit. And in fact, so I usually don't put papers of our group, but it's such a relevant to our class. I analyze this is from our group, but I usually don't. I mean, the survey paper may have out of 700 may have only 30 of our papers, so we're really 20 or something. So we're careful on that. But yeah, so you remember one of the challenge is that. And we saw this paper that I'm about to show again, just a reminder, is that a lot of very fancy multimodal algorithms say, we're doing nonlinear fusion, and we have those very fancy things, but at the end of the day, they seem to be additive fusion. They seem to take this complex one, and if you were to, in fact, integrate that over all XB, either within a batch or within a training set, and integrate over all of it, then you get FA, that's an approximation of FA, and then you take the same output and integrate over all the XA, then you get XB, and then if you take the sum of it, you get that nice projection. That's what we talked about a little while ago, and I think Paul also reminded you maybe of that during the quantification. And what was cool there is that is like all those fancy algorithms, they're very fancy, they have really good performance, but somewhat their unimodal, their additive version was performing almost as well as the very super complex nonlinear. And that paper had a few other it just reminded people to always have additive fusion as a baseline. That was one of the but the main thing was that there's very small difference between the EMAP and up. So then the question is like, how to be sure that I learn a model that has bimodal, nonlinear bimodal, and nonlinear trimodal interaction? How do I get sure that my model doesn't always learn unimodal? And that's the question. It's like you would like, if you have three modality and you're making a prediction, you would like to be able to factorize it into how much of the so the paper they're doing the full one, like the integral over all of it, so it would be hard. So they do an approximation. Usually they in their training or test sets, you think maybe on the test set, if the test set is not too big, instead of an integral, they do a summation over all of the XB of the training set. So it's an expected value over all of the XB of your test set that you have. If your test set is too big, you subsample randomly out of it to get an approximation of it. Yeah, I know so maybe Paul did Paul present that again? Okay, but yeah, so that it's a cool paper. I really like it. We built a lot from that, so it's a nice. Any more questions? Also, really happy to discuss. But yeah, so how can we, instead of having just the unimodal, which all those they like machine learning, like model deep learning, if there is a shortcut, they're gonna go for it, and then they may get stuck there and not be able to learn. And that's a little bit the issue of the previous one. Like if something works well, and then you keep re-emphasizing what works well, the other option don't get it. So really what you would like is get three outputs. One is based on the component that's unimodal, but you also would like, what is the component that's bimodal, where the real non-additive is happening? Something that where the two interaction, the only way to get that is the nonlinear representation of those two, and the trimodal. That's what we want. In fact, if you're not careful, like let's say you train like what is the first version of it, and we did it. In fact, we in fact have papers like that tried this. It's like the first version of training this is simply take those three classifiers and do an additive, and that's the unimodal. So that part is easy. The next one is you could think that, hey, I'm going to do bimodal by training three bimodal models. That sounds kind of obvious. Like I'm going to train bimodal with each of them. The problem with this is that there's nothing stopping that model to learn unimodal components. That there's nothing. In fact, the same is true in this one. There's nothing stopping that trimodal, although yes, it has as input three modalities. There's nothing stopping it from learning just one modality. And we've seen that because when we do EMAP of this, we find out that it's primarily unimodal, or at least equivalent to it. So how do I force it that it's only bimodal and it's only trimodal? That was kind of the thing. And the idea we came with turned out simple is good, huh? And once I say it, you're going to be, yes. The prioritize simple first. Start with simple first. So what is it, like the exam razor kind of a principle? What it means is first, start training this one. Train it as much as you can, or up to a certain point. At least train this. And now see how well you perform and use that residual and train this one just on the errors that this one is making. So the bimodal here is only going to train on the errors of this one. What does it mean? Is that if unimodal was successful in picking up all of your errors, all of the signal that it can pick up from unimodal, then you can go ahead and train the bimodal, and then go ahead and whatever is the residual that the bimodal did not, then put it in the trimodal. Now you can train it differently. One is sequential, so you just train all this one as much as possible. Then another one would be batch version. You do some batches of unimodal, some batch of bimodal or trimodal, and then you can do jointly. There's different version of that. But the general idea is to be a residual of each other. So when you train this one, you train on the residual where this has been frozen. You don't update this. And when you train this one, it gets frozen. That's the idea of this. When you do it jointly, you need to, this play of freezing things is needed on that. So what I showed here is during the training. So at that point, you do have labels. And at test time, you just use the three models that you've learned. So the final prediction is going to be the summation of those three. So it's more parameters, and that's something to think about how to do this in a more parameter efficient way. Right now, you end up 7 times more parameters, not exactly, but it's a little bit less than that because these models are smaller than this one. But you're definitely increasing, at least doubling the number of parameters. But what you get is uni, bi, and trimodal explicitly. So this by itself is not really a label. It's whatever increment to this so that's why you need to sum all three of them at this time. So it's not that it's related a little bit to bootstrapping. It's like, let's say that I have a batch, let's say for now, I have a training batch of 100 parameters, 100 samples. Let me do the simpler training version, which is serial. What it means is for those 100, I'm going to train this maybe over many epochs until the loss doesn't change. Like there's no more change in the loss. Like I kind of fit as much as I can for that batch, and then for the same 100. I'm gonna. My loss is still not 0 at that point. I mean, if it is, then you're done. So it's good, but it's probably not 0. So whatever is left of it, I'm going to start training this to have a new prediction. That's the new prediction, and that new prediction, it's not exactly right, but if it's a typical kind of loss, 1 minus the prediction of uni, that's kind of equivalent to that loss. So that's what I mean by residual, and that's that prediction needs to be close to each other, and then I go with for the next one. Yeah. Right. So that's a nice different way of thinking. We went through many iterations of that, so and there's a lot of future direction to be done. And then still in fusion, but then this one is like, I was not able to put it in one bucket. It's a fusion, it's a transference, it's a generation. It's all three of them together. And to do that, I kind of figured I do also a reminder. Some of it was also to remind you guys about some concept like autoencoder and variational autoencoder at the same time, and multimodal variational encoder, just to remind you. So autoencoder, that part is easy. You have an encoder function, many layers. You get a latent representation, and then you can generate this. But after learning, one of the issues is that if I take just the decoder and I look at the Z, and I randomly sample a Z in that space, I will most likely maybe get an image, but also that space may end up having a lot of holes. There's a lot of value of Z that in fact do not give me a good generation. It's just, there's nothing in this that constrained the Z space to not have holes in it and be used for generation. So that's not the only reason to do variational autoencoder, but that's one of the reasons, is that now you're no more going to predict Z, but you're going to predict a distribution over Z. And that part you've probably seen that is like that usually it's Gaussian. So you have, it's no more like you predict a Z, you predict a Gaussian, so a mean and a variance over it. And why would you do that? There's many reasons, but one of them is that if you do that, then you can force your model to be, in fact, that distribution to be a specific distribution. An example here is a centered Gaussian with a standard deviation of 1, a variance of 1. And then you can force that distribution to be equal to that. What do you end up doing by doing that? Is that now Z, I know after training my encoders and decoders that I can go back and sample anywhere in this, and I'm going to get a valid image. I'm going to get a valid image because I force this Z, this distribution of Z, to be around that. I force it there. So now I can go and sample for this, and I can do really cool things like morphing. I know I'm older, but there was a cool, in my young, there was a Michael Jackson and black and white video clip, and then he changed appearance. If you've not seen it, that's your homework tonight. But it was one of the first warping. At that point, it was, oh my gosh, they're warping the face. And now they do it all the time. In fact, you can do it for your homework tonight in probably 3 lines of code in PyTorch. But yeah, at that point, it was really cool. I don't think they were using variational autoencoder for that. But now you can do a Michael Jackson video clip if you want. So now you can regenerate images, you can translate. It's really cool. Multimodal variational encoder. And when you look at it in a graphical model, the main thing from a graphical model perspective is the decoder. Like that's your main probability of my X given my latent space. But we also learned the encoder. That's kind of what we end up also doing. So if you want to do multimodal, the simple way is to have one Z that generates both. Okay. So if I produce a digit, I move my lips and I say some words, but the digit is kind of my latent space. The problem with this is how do you fuse the encoders? So the generative is good, one, and then it becomes many. The problem is the other way around. I have many encoders that all get to come to one Z. How are they going to all come to go on one Z? And so there are many approaches. I'm presenting one of the somewhat simple but still work well is the product of expert. Is that you have all these encoders for visual and acoustic and all this, and all of them has a mean and a variance. And what I do, I just a product of expert, like I have all those Gaussian, and I just multiply them, and that gives me my final Gaussian, which is mostly my Z. So I know it looks really complex, those multimodal variational autoencoder. And most of it is simple because these are just generator, the same as a variational autoencoder. It's just that they had to find an not ad hoc, but somewhat ad hoc way of generating and putting them together. There've been since then some more complex, but I just wanted to give you a nice example of that. So now, if I have, so this is another way to just plot that same thing here. I'm just plotting is that I have all those variational autoencoder for each modality, and I find a way to combine it. But the problem when you learn this is that these encoders are kind of all separate. Yes, they have the same Z, but it's a product. They're not really learning from each other. They're not. And so, they may be not robust about missing data. That's another issue. So there's two things, is that they're not really learning from each other and they're not missing it. So in transference, when we talk about transference, we talk about translation, okay? And so the next paper I'm about to present could have been called Learning Multimodal VAE through Cross-Modal Translation. That's how I will have called the paper. But I call it differently, is through mutual supervision. But it's through cross-modal translation. So that's why I say it's a fusion, it's a generation, it's a transference, because it's all three of them together. So what they're saying is like to train that Z, instead of seeing Z just as generating this image and text separately, and using a product of, for the encoders, just a product of expert, I say, let's learn by translation. How is the information going from the image to the text and the text to image? So your loss will have two components. Your elbow loss, like often is based on elbow, will have two of them. One that goes from text to, so at the end of the day, you'll have a generation. They call it generation, which goes from text to image, and a captioning. And why they're not exactly the same, there's just a minor, but text it's kind of easy to have a language model and have that PT. On the image, it's a little bit more. So that's my hypothesis on why they didn't, like, why it's not exactly symmetric, but yeah. So, but yeah, the general idea is that your loss is going to learn Z, but learn Z is not because you have two image and text and they get the same Z and then they regenerate themselves. It's because you go from a text to an image and image to the text. You're kind of forcing the cross aspect of the generation. And their claim is that by doing that, you exchange more information, but also you're more robust for missing data, because suddenly the text is able to hallucinate the image more because you made it part of your loss to translate, and your image is able to hallucinate the text because you made it part of your loss. So then you can do generation as well. I talk about it as a representation learning, where the most important in my mind are the encoders. But that's for representation learning. But here, the most important may be your decoders, because you want to go from Z to that. Yeah, CycleGAN will have been, and I suppose there's a paper like this. If not, you should write it. Cross-modal translation through CycleGAN. CycleGAN will be another. Here, they wanted to do it through multimodal variational autoencoder view of it. But in fact, there is I don't know if Paul presented his own paper, but Paul, with in fact a project in this class, there was a project which was learning representation through translation. It was about 3 or 4 years ago. That kind of idea was not true. It was a simple feed-forward network. It was not like through autoencoders, but the general idea of learning representation through translation. He had done something. So I think you could do it through the MVA, and that's what they did. I think the main novelty was the idea of learning representation through translation was not completely new, but doing it in that VAE kind of case, where the nice thing is the the loss has a nice justification with the two elbow terms. And so I think it was more the math around that was cool. But doing it through cycle GAN will be another way to do that. Yeah. I suppose they compare with that, but I don't remember. Yeah. But yeah, so that brings together transference, generation and representation are two sides of the same coin. Yeah, good, I got it. Two sides of the same coin, really, because representation and generation are really related to each other. Good. So finally, no, not finally, but another problem is discretization. Like we often have like those speech representation, and we kind of arbitrarily or any kind of signal is like language. And also I tell her, it's like I love language. And I tease my NLP friends now that they also I'm an NLP department, so I have to accept that I'm an NLP researcher. But language is easy. Yeah, I will say it. Okay, I've said it. It's recorded now. You can go. But now, what part is nice is like language has those explicit tokens. They're like, this is a token. This is a word. This is it. Like segmentation is like 95% there. Yes, there's some issues, but like image signals like all the brain and all this, like very, I don't know, complex for segmentation. Now, language is complex for other reasoning, really interesting aspect. But for segmentation, it's a relatively easy thing. I mean, there's still like what a phrase, there's grammar, there's syntax, there's really interesting problem. But at least the basic unit, at least you know what your basic unit is. While in speech, you don't have that. So okay, now that you can take that, put it on YouTube and say LP thinks NLP is easy. Great. That's the other complex thing. So yeah, but yeah, so for object, people have started like saying, oh, an image is in fact just a list of objects, but it's a simplification. And the same way for medical imaging, for signal, it's hard. So the paper that one of the examples that I showed to do that, it was like, hey, why don't you take this and I presented that paper already. Just a small reminder is like, why don't you just see the distributional hypothesis, this idea of BERT, but just put it into signal, but then mix that with just simple clustering. So take my signal arbitrarily. It doesn't solve the whole problem because I arbitrarily put some window size, which is a hyperparameter, which would need to be done. But then I cluster it, and then the goal is then for my BERT model will be not to predict the next token, which is a typical language model, but then it's going to be to predict the cluster ID. And so I will do the typical BERT, just hiding some things, and then find a way to predict the clusters. Now, I'm presenting the next paper. It's just someone had to do it. Like if I tell you someone just did an audio-based BERT, Hubert, what is the next paper that has to happen? An audio-visual BERT. Yeah, an audio-visual Hubert. It has to. So yeah, there is one. I had to present it. It's one, and there's always a lot of the details because sometimes you think, oh, it's simple, it's a low-hanging fruit. As an advisor, you're like, hey, this is a low-hanging fruit. Why don't you go with it? And then the students spend another 6 months because, yeah, it looked low, but it's not that it was fucked up. There was a few other things. I had to go get a ladder first, and I had to get scissors first, and I got a few other things before I get there. So the paper has a few of those extra details. I'm just going to give one of them. But the main thing is the basic is the same. But instead of clustering just based on one modality, you do clustering over two modalities. And I believe they didn't go too complex on the clustering, keep the same. You can probably also improve that eventually by locally do some kind of alignment of the two spaces before doing the clustering. So because doing a good clustering over two modalities is a little bit debatable, but yeah. But I told you that there's always a few extra things. One of the things was that it was really important for them to do some kind of modality dropout so that the model turned out to be really good at audio Hubert, at visual Hubert, or at both of them. So they randomly, with some probabilities, either do the audiovisual or just the audio or just the visual, just a modality dropout that they added to this. So I don't know, I had to add it to this. Coordination, you remember we spent quite a bit of time talking about contrastive learning. And this is representation coordination mixed with quantification. I really like that paper for that. It had a nice thing. So typical contrastive learning, you have paired data, like image and text. And because you have paired data, then anything that's not paired, you could call it a negative pair. And that's how a lot of the clip and all of these are learned. And so contrastive learning, bring closer the positive, put away the negative. And this is the equation I introduced when I talk about clip. This is like positive pairs, you want them to be close, and negative pairs far. And often the positive pair may be part of it, but it's so few that the negative pair take over. The thing I didn't I said, oh, this is a cosine similarity. The thing I didn't do, I mean, these are the kind of details that at some point I don't go in all of it, but there's a temperature term in many of them. And like I told you, any model has a hyperparameter, like this is almost every, so the clip and many of them will have, and so cosine similarity often will have like, in a sense, it's like a temperature is like, things that are close, really close, or things that are far are very far. You're kind of pushing, in a sense, you're putting more weight on your mistakes or not. Like, do you want your mistake? Or and you can usually, that allows you to do bigger step. But then, as you can imagine, usually you want to reduce maybe temperature as you go closer to your solution. So I'm saying that because we're going to reuse it in a little bit later. But the really interesting finding, and that's why it's a quantification paper, is that you train these models, and your whole goal was to bring the two spaces together. You remember blue car minus blue plus red? And I told you, you cannot do all arithmetic. There's some that works and there's some that won't work. Especially you have to do an image minus a word plus another word, and then you get an image embedding, because and they showed it visually. In fact, if you look at all these pairs of text and image, although you work and spend a lot of time on contrastive learning to bring them into what everybody thought was the same space, kind of, it turned out that no, clip, blip, video clip, virt, clasp, all of them, they all do end up learning a line space, but not overlapping space. They're not overlapping. There's a small gap, and that's what they emphasize. I forgot if it's there, but the idea of modality gap, that the two embedding, you remember when you do clip or something, you learn two embeddings and you coordinate them. So they end up being separate. So that's both interesting and troubling. And like, why? I mean, I thought the whole loss was that I will bring the similarity close to each other, that will that was the whole thing of the contrastive. The positive would be close, and these are positive pairs. Like, so the positive pairs should be close to each other, should be overlapping. You will think the two of space. And so they tried to explain, and they found at least two main things, three findings, but two main reasons. The first finding is not really about the modality gap directly, but it's really interesting. It seems to be general over most deep learning. That's at least the claim, and then maybe so what's really interesting is let's just train for now a bird or a visual BERT, like not visual BERT, VIT, visual transformer. So forget multimodal for now, for a second. Just train it. And I train BERT, and I take every pairs with all other pairs and any pair of words, and I just see the similarity function between them. And what they find is somehow their first hypothesis was that when you do that, most words are somewhat close to each other, and then there's kind of a distribution over zero. But no, it turned out to be a cone. It's like when you do a cosine similarity between the two words, like you learn a BERT, and then you have two words, and you see the cosine similarity, you will expect this to be over zero, like kind of maybe Gaussian or half Gaussian or Poisson or something. I don't know. But no, zero is almost not there. Even two words that were supposed to be the same seem to be somewhat of there's a gap, like the zero come later. And that was the first observation that was really interesting. So that these models, although they claim to learn a space where things are close to each other, they do, but somehow they give themselves a little bit of space. And then they're learning around that hyperdimensional cone. It's hyperdimensional also. And then so that was an initial but the second thing is that and that one is one of the reasons, or at least their hypothesis of why there's a modality gap, is that if you train two unimodal, or in fact two model, let's say like simple product of expert, like you have two encoders that are merged together, like additive fusion, any of them, just because the fact that you have two and both of them are initialized randomly, they're gonna learn within their neighborhood. So that's the reason. One of the hypotheses of why there is a gap is it's not that they are multimodal. Even if you do it just with English text, and you learn, let's say, a multi-headed bird. I don't think they try exactly that, but like the multiple head of bird, like both of them are randomly initialized separately. The fact that they're randomly initialized separately, they're gonna live in their own world. Yes, they're gonna try to get closer, but their hypothesis is that they're not going to live super far. They stay a little bit in that. So where the fact that they were randomly initialized in different part of the space makes it that the gap will somewhat stay a little bit. So that's one of the reasons. That's not the only reason, but that's one of the hypotheses of the paper. That's an interesting. And then the last one, which is now let's go back to contrastive learning. It turned out that contrastive learning has that hyperparameter, that temperature, and usually it's set once, like so very high temperature, and it turned out that as long as you keep some temperature, that what it is this is you learn like language and vision to clip. You train a clip, and then you look for any pair, any positive pair on my data set, and look at the average distance, and look average distance of the pair. In fact, sorry, look at the test set, the validation set. Here it's in the validation, and look at every pair of data. Sorry, I thought it was only the positive. Look at every pair of data and look at the distance between that. And look at the validation loss. Like you would like the distance to be the closest to each other, like two pair, like two text and an image to be close to each other when the loss is zero, like the lowest. When the loss is the lowest, you would like, but no, there's a gap. But if you put the temperature to 1, like no temperature, so the contrastive learning, the similarity, the cosine doesn't have, somehow you get with the validation loss that does have 0. So somehow, for good reason, people were putting temperature in their clip because they wanted to give better validation, and probably this is probably lower. Yeah, it's lower than the you see, this is worse performance. So you don't get as good performance if you go with the temperature of 1. So there's a reason you put the temperature there, you get better learning. But it came at the cost of somehow having this weird modality gap in between them by having more temperature. So I don't know. That was an interesting finding. This one was more of a quantification paper, but nice one. Let me go for maybe one last one, and we'll see. This is more of an easier paper, but it was just a cute one, more about interpretability and generation. So the idea is like, what if I could not only generate images, but generate an image with having an initial draft of the layout that I want. So I want an image with a bed, with pillows, with a window. In fact, I want the window right there, or something like this. And then you can generate it or generate it, in fact, with different styles. This is just a typical GAN we talked earlier. So typical GAN is I have my latent space, I'm generating an image, and then the discriminator decides, is it able to generate it or a real one? And so what they will do is say, hey, this is the typical one. What I want is integrate this extra step, this middle step, which is kind of a draft of this. And now you can say, how do I generate that initial draft? Maybe by hand. I think they even have experiments like this. Or I have multiple objects, and then I'm going to iteratively generate my sketch iteratively. And once I'm done iteratively for all objects, then I will generate the final version. So if you do that, the problem is like, how do you know that these sketches are valid? So then what they did is add a loss, sorry for the animation, but it add a loss that says, hey, this is a real image. Let me create an algorithm that is kind of easy, or somewhat, if you have object segmentation solved, or you manually do it on a subset of image. And then from that, I can just ensure that for these where I have the layout, that this is correct. But, and that's where the paper goes a little bit more in details, that's their choice, is that they added another loss that says, I want to be sure that my object are designed or generated the way I want it. And finally, everything gets a little bit complicated. I want to be able to have different styles in it. So I split my latent space into structure, which is the layout, and to the style. Anyway, so what's really nice is you get a layout, you generate it, and you can generate also iteratively this. So for the last few minutes, I will just show a few benchmark data set. Just an example. So I think I may have mentioned it at some point, but if you don't know, Ego 4D. For many of you who are at LTI, you've heard it maybe from Jim Ray. This is a huge effort. Kristen Groman and others at Facebook help manage it, but the effort is over many countries and over many universities. The idea was to have ego motion. So ego motion means usually most of the work before that was a camera looking at the person. Now is the idea, especially, I don't know, some people will believe in this future where glasses have cameras looking back. We know from Google experience that we have to be careful with these experiments, but there is a chance that we'll end up with those augmented reality glasses at some point. And so And we already see them for policemen, policewomen. They will wear these, and we see it at other places. So understanding from that view, because suddenly it's no more you see the person, is like you have to understand the person from a very distant way. You don't see them explicitly. So there they studied a lot of interesting, I would say they're kind of basic thing, because they're like, the problem is so complex, they're starting with simpler. So finding in that video recording, that could have been done in any video data set, doesn't need to be ego. Is like finding, like if I say in the video, find a scene where he got killed, or where they met the first time. And so you can go and find it, find object and hand. And the audioization, when I say basic, like audioization is important. And this one is interesting, is forecasting. I see the video up to now, what is likely to happen in the video moving forward. And the last benchmark is a QA, but that one is about science. But the part that I like about it is they call it thought chain. And that's so it's no more just question and answer. You have question answer in some context, but you have the answer, but also you need to have like kind of an explanation, a thought of why you think that this is the right answer. And they have a format for that, where you have a question, you have maybe some context, and then the answer is this with the thought process of that. And there was also Google doing smell as a modality. Yeah. So thank you all for these last 12 weeks. Take a good break for Thanksgiving. Start working on your project if you've not now started working now. If you're interested to meet, I will send a note later today. I think Monday and Wednesday, I should have some times for meetings with teams. Otherwise, good luck with the project. After Thanksgiving, we'll have the two guest lectures. Thank you.